Welcome to EDU World Space.
In this problem, we have an astronaut in space who is attached to her spaceship by a massless cable, and she pulls on the cable, and we're asked a few questions about what happens. So to solve this problem, we'll just need a few basic concepts. We'll need to keep in mind Newton's third law. So when we have a force applied, there's always going to be an equal and opposite reaction force. Newton's second law, so when we can relate force and acceleration by F equals to ma, and the concept of tension, that force can be transmitted through a cable or rope. So for this problem, we are given our mass of our astronaut is 105 kilograms. Mass of our ship is 9.05 times 10 to the fourth kilograms, and our force applied is 80 newtons. So our situation is going to be, we have a big mass, M, connected to a smaller mass, lowercase m. And so there's going to be this applied force F. And so at each point, we're going at each point of connection, we'll have two reaction forces here. So we'll have this equal reaction force going this way. And then at the spaceship, we'll also have equivalent forces opposing. And we'll have, and throughout, there will be a force of tension transmitting the applied force from our astronaut. Okay, part A asks us what is the force of the cable on our astronaut. So the force of the astronaut on the cable is going to be equal and opposite, right? So we use our third law. Force of the astronaut on the cable, which we know is equivalent to force of the cable on the astronaut. So equal and opposite reactions here. So our cable is going to exert equivalently an 80 Newton force on our astronaut. Part B asks us, how can a massless cable exert a force when we know, according to Newton's second law, we need a mass to relate force and acceleration? That's accomplished through tension in our cable. And tension, which in a rope or cable allows a force to be transmitted. And we say for this idealized situation, our cable is massless. If we accounted for mass, we would have a similar situation, but slightly more complicated, as the tension would vary throughout the length of the cable according to its mass. All right, so yeah, part B, so tension allows our massless cable to transmit force. And part C, what is our acceleration of our astronaut? And so we can get that from F equals ma. So our net force on our astronaut, we found to be 80 newtons. And so that's going to be equal to mass of the astronaut times acceleration. So we get acceleration equal to 80 newtons over 105 kilograms, mass of our astronaut. And so we find her acceleration to be 0.762 meters per second squared. Part D asks us what is the force of the cable on our ship. And again, we're transmitting, because we have a massless cable, we're transmitting the same force everywhere. So it will be 80 newtons. If we accounted for the mass of the cable, then the tension and the force transmitted to the ship would vary, but we're not adding that complication in just yet. And part E asks us what is the acceleration of our ship. And so again, net force on our ship is 80 newtons. So that's going to be equal to mass of ship times its acceleration. So acceleration of our ship is going to be 80 newtons divided by its mass, 9.05 times 10 to the fourth kilograms. And we will get a small acceleration, 8.84 times 10 to the minus fourth meters per second squared, and which, as we expect, the